Section: Introduction. In this section, we discuss volumetric videos, which capture dynamic scenes from various angles and allow users to interact with virtual objects for an immersive experience. High-quality volumetric videos are essential in fields like augmented and virtual reality, gaming, and telepresence. Traditional systems have produced impressive results but often require specialized hardware and complex setups, making them less accessible. We note that new neural rendering techniques can create realistic views of dynamic scenes using four-dimensional representations. Early efforts focused on using neural radiance fields with time-based data, but these methods had limitations in quality and efficiency, resulting in slow render times. Recent advancements have utilized more robust four-dimensional representations, like feature grids or point clouds, to improve rendering quality, but they typically work only with short video sequences. When applied to longer videos, these methods demand large models, which can be challenging due to storage constraints. To address these issues, we introduce the Temporal Gaussian Hierarchy, a new four-dimensional representation designed for efficiently modeling long volumetric videos. Our key insight is that dynamic scenes often contain areas that change slowly and areas that change quickly, allowing us to exploit this temporal redundancy. Our approach creates a multi-level hierarchy of scene elements, such as three-dimensional or four-dimensional Gaussian splats, to represent these scenes. Each level of the hierarchy corresponds to different rates of content change, allowing us to manage the number of scene elements effectively. We demonstrate that in our hierarchical model, areas with slower motion can share Gaussian elements across longer time frames, reducing the overall number of elements and the model size. Additionally, the Temporal Gaussian Hierarchy enables us to represent scenes at specific moments using only a subset of segments, further minimizing memory usage during runtime. This structure allows for efficient training and rendering, regardless of video length, as we can quickly access the relevant segments in memory. To further optimize our model size, we introduce a hybrid appearance model that combines diffuse and view-dependent Gaussians, which adaptively allocates representation power to different scene areas. This approach helps prevent overfitting while maintaining the ability to model dynamic appearances effectively. We also develop a GPU-accelerated algorithm and a hardware-optimized rasterization pipeline to significantly improve rendering speed. Our method outperforms previous techniques in training costs, rendering efficiency, and storage requirements, while delivering superior visual quality. We evaluate our approach on various datasets for dynamic view synthesis and collect long multi-view sequences to showcase its scalability. Our results indicate that we achieve state-of-the-art visual quality and rendering speed with lower training costs and memory usage, enabling the effective reconstruction and rendering of long volumetric videos. Using an RTX 4090 GPU, we can process videos with 18,000 frames at 1080p resolution, achieving a rendering speed of 450 frames per second. We also gather a long real-world multi-view dataset, named SelfCap, to validate our method. In summary, we present a novel, efficient, and expressive temporal Gaussian hierarchy representation for long volumetric videos. To our knowledge, our method is the first capable of handling minutes of volumetric video data. We propose a compact appearance model and a new rasterization implementation to support real-time, high-quality dynamic view synthesis while maintaining a compact size. Our system efficiently models long volumetric videos for the first time, demonstrating state-of-the-art dynamic view synthesis quality on various datasets, along with the best rendering speed and reduced training costs and memory usage. Section Summary. In this section, we introduce the Temporal Gaussian Hierarchy, a novel 4D representation designed for efficient modeling and rendering of long volumetric videos, addressing the challenges of storage and processing speed. Our method significantly enhances rendering quality and efficiency while reducing training costs, enabling the handling of minutes-long video sequences with state-of-the-art performance. Section: Related Work. In this section, we discuss related work in volumetric videos and neural scene representations for dynamic scenes. Volumetric videos capture dynamic scenes from various angles, allowing for immersive viewing experiences. Earlier methods used techniques like shape from silhouettes and depth sensors, while some explored combining skeletal structures and body shapes for 3D reconstruction. However, many of these approaches struggle with complex scenes, require specific templates, or depend on costly capture devices, limiting their real-world use. Neural scene representations have gained attention for their effectiveness in 3D reconstruction and view synthesis. Techniques like NeRF and SDF use neural networks to represent scenes, but they often face challenges with dynamic scenes due to lighting changes and object movements. Recent efforts have tried to adapt NeRF for volumetric videos, but many methods can only handle limited camera movements and object dynamics. Some approaches use 4D NeRF, which incorporates time along with spatial data, but they can be computationally expensive and may not produce high-quality results. To improve rendering speed, some methods use simpler structures like voxel grids or point-based representations, which reduce computational demands but can increase storage needs. Recent strategies have looked into weight decomposition to save memory, but these often struggle with effectively representing dynamic scenes. Our approach introduces a temporal Gaussian hierarchy, which efficiently scales to high-resolution volumetric videos while ensuring real-time rendering. We also explore Gaussian splatting for dynamic scenes, where 3D Gaussians are used to reconstruct high-fidelity scenes. Previous methods tracked 3D Gaussians frame by frame, leading to large models for long sequences. In contrast, we utilize varying segment lengths to share temporal information across frames, minimizing storage requirements. Other studies have attempted to learn the motion of 3D Gaussians, but sudden movements in dynamic objects pose challenges. Our temporal Gaussian hierarchy allows us to use a specific set of 4D Gaussians for dynamic scenes, maintaining low memory costs during training and inference. This design enables effective scaling for long volumetric videos. Overall, our goal is to create a compact and efficient 4D representation from multi-view videos that supports real-time playback. We developed the temporal Gaussian hierarchy to model motion dynamics, propose a compact appearance representation to reduce storage costs, and establish an efficient rendering pipeline for real-time performance. Section Summary. In this section, we review existing methods for volumetric video capture and dynamic scene representation, highlighting their limitations in handling complex scenes and real-time rendering. We then introduce our temporal Gaussian hierarchy, which efficiently models dynamic scenes with reduced storage costs and improved rendering speeds, enabling effective playback of long volumetric videos. Section: Temporal Gaussian Hierarchy. In this section, we introduce the temporal Gaussian hierarchy, a new approach to volumetric videos that addresses the high GPU memory and time requirements of previous methods, which often increase with video length. Our design utilizes a tree-like structure to manage different motion granularities, allowing us to efficiently identify relevant segments for any given timestamp while keeping computation costs stable, regardless of video length. We provide an overview of the temporal Gaussian hierarchy, which accommodates varying motion scales in dynamic scenes. We create a hierarchical structure where each level contains multiple segments of equal length, with the segment length halving at each deeper level. For example, if the total video duration is 10 units, the hierarchy depth is 1 unit, and the root segment length is 2 units. We also include a global segment to capture static parts of the scene. Within each segment, we store sets of 4D Gaussians to represent dynamic scenes. Each 4D Gaussian is characterized by its mean, scaling, opacity, 2 isotropic quaternions, base color, and spherical harmonics coefficients. The 4D covariance matrix defines the Gaussian distribution, and the opacity follows a Gaussian distribution centered around its temporal midpoint. The temporal Gaussian hierarchy is designed to effectively model video dynamics, using longer segments for slow motions and shorter segments for fast motions. We ensure that the segment range covers the Gaussian's influence radius and is not overlapped by segments at deeper levels. We calculate the start and end timestamps for each segment and strategically place the 4D Gaussians to optimize their positioning. For efficient rendering, we sample the 4D Gaussians that affect a specific timestamp. Since segments at each level do not overlap, we only consider one segment at a given level, which simplifies the identification process. We then combine all relevant 4D Gaussians to render images using a differentiable rasterizer. By storing the temporal Gaussian hierarchy in RAM and only transferring influenced segments to GPU memory, we significantly reduce GPU memory usage and maintain consistent performance, even for long videos. This method avoids the memory inefficiencies of naive approaches and allows for parallel processing during rendering, ensuring speed is not compromised. Section Summary. In this section, we introduce the Temporal Gaussian Hierarchy, a novel 4D representation that efficiently manages hierarchical temporal segments to maintain nearly constant GPU memory and computation costs for volumetric videos of any length. By utilizing a tree-like structure to accommodate varying motion granularities and strategically placing 4D Gaussians, we enhance rendering efficiency while minimizing memory usage. Section Hierarchy Update. In this section, we update the hierarchy after each training step by optimizing the properties of the streaming Gaussians using reconstruction loss. This results in a new set of Gaussians with different influence radii. We then reassign these optimized four-dimensional Gaussians back into their respective levels and nodes in the hierarchical structure. For each updated Gaussian with a new opacity distribution, we calculate the influence range using the same opacity threshold. We also compute the indices for the start and end influence timestamps for each level of the Gaussian hierarchy. By comparing values, we determine if the Gaussian can adapt to a specific level, defining the updated level as the maximum level that meets this condition. Since our update algorithm works on levels rather than individual segments, the computational complexity remains manageable, helping us maintain constant memory usage and iteration speed. Next, we address the storage overhead caused by the large number of spherical harmonics used in the original 3D Gaussian splatting model. To tackle this, we propose a compact appearance model that uses sparse spherical harmonics to efficiently capture view-dependent effects while reducing model size. We note that the diffuse part of the volumetric video does not need high-degree spherical harmonics for accurate modeling, so we exclude these Gaussians to save storage. We initialize the residual spherical harmonics of all Gaussians to 0 and apply a gradient threshold to identify and retain diffuse properties. For view-dependent Gaussians, we optimize them regardless of their gradient scale. We also monitor the proportion of view-dependent Gaussians and adjust the gradient threshold for future optimization steps once a certain ratio is reached. After training, we group the Gaussians based on their properties, which helps improve compression when using Huffman coding. For training, we optimize our model using the rendered and ground truth images, focusing on minimizing mean squared error, structural similarity error, and perceptual similarity loss. We also implement an adaptive control scheme to manage the 4D Gaussian ellipsoids, allowing us to split, clone, and prune them every 100 iterations. These updated ellipsoids can be integrated into the temporal Gaussian hierarchy. To enhance real-time rendering, we develop a new hardware-accelerated rasterization algorithm that combines CUDA-based sorting with graphics-based rasterization. We acquire the streaming Gaussians and sort them based on view space depth. These sorted Gaussians are then projected into screen space, transforming them into rectangular primitives for rasterization. The hardware rasterization pipeline efficiently computes the final color for each pixel using back-to-front alpha blending. Our approach significantly improves rendering efficiency, achieving a 5-fold speed increase compared to standard software rasterization. We have made this implementation open source for further use. Section Summary. In this section, we update the properties of streaming Gaussians after each training step by optimizing their influence radius and reassigning them within a hierarchical structure, ensuring computational efficiency. We also introduce a compact appearance model that reduces storage overhead by leveraging sparse spherical harmonics for view-dependent effects, while maintaining rendering quality, and we enhance rendering speed through a new hardware-accelerated rasterization algorithm that significantly improves efficiency. Section: Optimization. In this section, we describe our optimization process. We train our temporal Gaussian hierarchy representation using the PyTorch framework and custom CUDA kernels to efficiently update the structure. We utilize the Atom optimizer with a learning rate of 0.95, as referenced in 3DGS. Typically, we train the model for 50,000 iterations with a sequence length of 1,200 frames, which takes about 2 hours on an RTX 4090 GPU. We adjust the number of iterations based on the sequence length. Since different datasets have varying resolutions, the time per iteration can differ, affecting overall training duration. Following the methods in 3DGS and 4DGS, we adaptively control the number of Gaussians by splitting, cloning, and pruning them based on their gradients and opacity values every 100 iterations. Our efficient structure allows us to limit this control to only the segments sampled in previous iterations, which reduces GPU memory usage and computational costs. Regarding hyperparameters, we set them empirically based on sensitivity analysis or previous work. Specifically, we establish 9 levels in the temporal Gaussian hierarchy and maintain a root segment size of 96 throughout our evaluations. We set the opacity threshold for the marginal temporal Gaussian to 0.97. For the compact appearance model, we define the gradient threshold for separating diffuse and view-dependent Gaussians to 0.98 and the cutoff ratio to 1. We use 3 degrees of spherical harmonics for view dependency modeling, resulting in 9 basis functions. The weights for the mean squared error and structure and perceptual similarity loss are set to 0.8, 0.2, and 0.01, respectively. For initialization, we follow 3DGS by using sparse point clouds from the structure from motion process for each frame of the volumetric video. For methods with different initialization strategies, we ensure their initial point counts are at least equal to ours by upsampling their point clouds for fair comparison. We determine the initial 3D scaling of the Gaussians through k-nearest neighbor sampling on the sparse point cloud, calculating average distances as done in 3DGS. The temporal scaling is set to match the sequence time being reconstructed. We evaluate our approach using public datasets like Neural 3DV, NRF Outdoor, Mobile Stage, and CMU Panoptic, as they provide longer video sequences. Neural 3DV is a benchmark for novel view synthesis, captured with 19 to 21 cameras at a resolution of 270 by 1060 and 30 frames per second. We focus on the flame_salmon scene, which has 1,200 frames. We downsample the videos by a factor of 2 and follow the specified training and testing camera split. NRF Outdoor is a dynamic dataset of outdoor scenes recorded by 18 synchronized cameras at a resolution of 1920 by 1080 and 60 frames per second. We select 3 sequences, each with 1,200 frames, featuring 2 actors in an outdoor setting. We use 1 camera for testing and the others for training. Mobile Stage captures dynamic humans at 30 frames per second with 24 cameras, and we evaluate the Dance 3 sequence, which includes 3 dancing actors over 1,600 frames. We use 1 camera for testing and the rest for training. CMU Panoptic is a large-scale dataset capturing various human interactions. We select 3 subsequences from sports clips and follow the training and testing split of 27:4, using the full resolution of 31 HD cameras. Additionally, we create a new dynamic multi-view dataset called SelfCap, which includes 3 dynamic videos captured at 60 frames per second in 4K resolution with 22 synchronized iPhone cameras. These videos range from 2 to 10 minutes long, exceeding the lengths of previous datasets. By training and evaluating on these longer sequences, we showcase our ability to represent long volumetric videos efficiently. We plan to publicly release this dataset to support research in long volumetric video modeling. All datasets are captured with synchronized static camera arrays, and while we do not enforce explicit temporal consistency, we ensure the camera parameters are shared. The datasets primarily feature static backgrounds with dynamic foregrounds, justifying our use of the global segment and compact appearance model. Our representation is defined in the world coordinate system, so even with camera movement, the impact should be minimal as long as the camera parameters are known. Section Summary. In this section, we describe our optimization process for the Temporal Gaussian Hierarchy structure using PyTorch and custom CUDA kernels, employing an atom optimizer and adaptive control on Gaussians to enhance efficiency and reduce memory usage. We also detail our empirical hyperparameter settings, initialization methods using sparse point clouds, and the diverse datasets utilized for evaluation, including our newly created self-cap dataset for long volumetric video modeling. Section: Baselines. In this section, we include several advanced baseline methods for comparison, such as 3DGS, 4DGS, ENERF, 4K4D, and Die3DGS. We note that 3DGS uses explicit Gaussian shapes to model 3D scenes effectively, achieving high-quality rendering and speed, but it is limited to static scenes. To test its performance on dynamic scenes, we train 3DGS on a per-frame basis for the testing frames. Die3DGS enhances this by optimizing scene geometry and appearance tracking in a streaming manner. 4DGS builds on 3DGS by adding a time dimension, creating a 4D representation that captures both space and time, allowing for detailed modeling in volumetric videos. We also explore dynamic methods that use implicit and hybrid representations. ENERF creates a cost volume to predict rough scene geometry, guiding point sampling for implicit radiance fields. 4K4D incorporates dynamic point clouds and uses a hybrid appearance model to enhance rendering quality. We train the baseline models using the official implementations with different frame lengths. For 3DGS, we use a per-frame training approach. For 4DGS and 4K4D, we divide each video into 4 equal segments and train each segment separately. For ENERF, we fine-tune the pre-trained model on the entire video. To evaluate the quality of rendered images, we use metrics like PSNR, SSIM, and LPIPS. PSNR measures the difference between a reconstructed image and the original, with higher values indicating better quality. SSIM assesses structural similarity, ranging from -1 to 1, where higher values mean more similarity. LPIPS evaluates how similar images appear to human perception. We also consider VRAM, storage, training time, and rendering speed to illustrate the costs involved. VRAM indicates the GPU memory needed for training, while storage reflects the model size on disk. We find that baseline methods like 3DGS, 4K4D, and 4DGS struggle with large volumetric videos, so we train them on shorter segments and combine the results. When dividing a video into segments, both VRAM and storage requirements increase proportionally. Since 4K4D and ENERF need source images, their storage costs include these images as well. Training time shows how quickly each method converges, and we sum the training costs over all segments for 3DGS, 4K4D, and 4DGS. Rendering speed is measured in frames per second when rendering to a real-time interface. In our comparison experiments, we present both qualitative and quantitative results. Our method consistently shows the best or comparable performance across all datasets and evaluation metrics, including training cost, memory usage, speed, and image quality. Compared to Gaussian-based methods like 3DGS and 4DGS, our model has lower training costs, storage needs, and faster inference speeds. While 3DGS provides good visual quality through per-frame training, its VRAM and storage usage increases significantly with longer videos, making it less suitable for extensive volumetric content. Additionally, 3DGS often results in noticeable flickering due to its independent frame modeling. 4DGS improves on 3DGS by adding a temporal dimension but still faces high computation costs. In contrast, our model achieves an 80 times speed improvement over the implicit method ENERF, which requires expensive network evaluations for appearance modeling. ENERF also tends to produce blurry results around edges and occlusions in complex scenes, reducing visual quality. Although 4K 4D has a similar inference speed to ours, its reliance on point clouds limits its ability to deliver detailed appearances, especially in challenging backgrounds like those in neural 3DV. Like 3DGS, 4K 4D's per-frame modeling leads to flickering artifacts as well. Section Summary. In this section, we compare our method against several state-of-the-art baselines, including 3DGS, 4DGS, NRF, and 4K 4D, highlighting their strengths and limitations in rendering quality, training costs, and handling dynamic scenes. Our approach outperforms these methods in terms of efficiency and visual quality, particularly in managing long volumetric videos without the flickering artifacts seen in per-frame models. Section. Results on long videos of self-cap. In this section, we present our results on long videos using self-cap. Our experiments show that our method works well for videos lasting between 405 to 550 seconds. In contrast to earlier methods that only managed videos of 15 to 52 seconds, we see significant improvements. To further explore the capability for longer videos, we tested our approach on the self-cap dataset, which includes videos with 6,000 frames or more. Thanks to our temporal Gaussian hierarchy, we keep training costs low while effectively handling large volumetric videos. In our visual results from the self-cap dataset, we demonstrate high-quality reconstructions, especially in challenging areas with edges or occlusions. We also conducted an ablation study to analyze the components of our model using the neural 3DV dataset. The results of these analyses are shown in our figures and tables. For the temporal Gaussian hierarchy, we found that without it, our model retrieves all 4D Gaussians for each training frame, leading to high VRAM usage and slow training speeds. This inefficiency results in poorer rendering quality. When examining the compact appearance model, we compared results and found that our model uses only 40% of the disk space compared to one using full spherical harmonics, while still achieving the same rendering quality. This suggests that our model can be scaled to longer videos without significant storage issues. In terms of real-time rendering, our ablation study showed that our algorithm is 5 times faster than the standard rasterization pipeline, benefiting from quick hardware rasterization. We also analyzed the hyperparameters of the temporal Gaussian hierarchy as the number of video frames increased. Our findings indicate that while increasing the number of levels improves efficiency, too many levels can slow down the process. Therefore, we set the default to 9 levels. Our visual results show that coarser levels capture static scenes, while finer levels model dynamic objects. The length of the root segment is another important factor for efficiency. Our study revealed that increasing the segment length initially reduces training costs, but if the length is too extreme, it can lead to inefficiencies. We determined that a segment length of 101 to 113 is optimal for our experiments. Finally, we evaluated the training costs of models with and without the temporal Gaussian hierarchy as the number of training frames increased. Our results indicate that the temporal Gaussian hierarchy maintains consistent VRAM costs and iteration speeds, even with long video frames, while the alternative incurs much higher costs. This scalability is crucial for training long volumetric videos effectively. Section Summary. In this section, we demonstrate the effectiveness of our method on long videos, achieving significant improvements over previous techniques and maintaining low training costs through our temporal Gaussian hierarchy. Our experiments show that this approach allows for high-fidelity rendering of extensive volumetric videos while optimizing VRAM usage and iteration speed, even as the number of video frames increases. Section. Ablations on appearance model. In this section, we analyze the effect of the ratio parameter in our appearance model. We look at how different gradient ratios impact the disk storage of our models. Specifically, when the ratio is 0, we only use the base color for diffuse appearance, while a ratio of 1 allows us to use all spherical harmonics coefficients for view-dependent effects. Our findings show that as the ratio decreases, the storage cost also decreases, but this comes with a reduction in the ability to model view-dependent effects, leading to lower image quality. We found that a ratio of 0.15 significantly cuts down storage without affecting rendering quality. We also examined the influence of various gradient thresholds when using residual spherical harmonics, selecting a threshold of 0.000001 for our method based on our experiments. Additionally, we compare the view-dependent effects across different models. When the spherical harmonics coefficients are set to 0, the rendering only shows a diffuse appearance without any view-dependent effects. Our sparse spherical harmonics representation maintains the ability to express view-dependent effects similar to the full representation while greatly reducing storage, showcasing the effectiveness of our compact appearance model. Next, we evaluate the performance of our hardware rasterizer against the original software rasterizer, as well as the impact of different sorting backends. This evaluation is conducted on a high-end machine equipped with an RTX 4090 GPU and an i9-13900K CPU. Our results indicate that using the CUDA backend significantly enhances GPU utilization and sorting throughput, leading to improved rendering speed compared to CPU sorting or compute shader sorting backends. Finally, we visualize the distribution of 4D Gaussians across different levels of the Temporal Gaussian Hierarchy and present the rendering results for these levels. Our visualizations reveal that while the segments in the Temporal Gaussian Hierarchy are uniformly divided, the number of 4D Gaussians in each segment varies, resulting in a non-uniform distribution of representational power over time.